Hi everyone. Let's do those FRQ practice problems. Here's the first one. The crane is hoisting a load of mass 1 equals 500 kilograms. That's down there. The load is supported by a hook of mass 2, 50 kilograms, and it's lifted upwards at a constant acceleration of 2 meters per second squared. Great. Hey, what do we know about that? We know the net force is going to be pointing up. That's what that means for us. So we're going to draw and label the forces acting on the hook and the forces acting on the load as they accelerate upwards. So if we look here, we've got, this is the hook. We've got tension pulling it up, tension pulling it down, and of course we've got the force of gravity. So let me draw Fg equals mg. So mass is 50. 50 times 10 gives us 500 newtons. All right, and then I'm going to put the tension. It's tension 1 that's pointing down. T1. I'll put F. I'll call it FT1. And then, like I said, we know that the acceleration is pointing up, the F net's pointing up, so I'm going to make FT2 longer than FT1 and FG combined. Okay. All right, let's look at the load. We've just got tension 1 acting on the load and gravity. So Fg equals mg. That's going to be 5,000 because the load is 500 kilograms. And then we know that Ft1, see, I didn't do a good job of this again. Oh well. Ft1 is going to be the same as Ft1 over here. So honestly, here's what we're going to do. This is just going to become very big. Goes all the way up there now, Ft2, because I need to make Ft1. Ft1 is the same, so I need to make Ft1 about that long. Okay, great. We're doing our best here. We're doing our best. Okay, I'm going to come back to this. It says, then it asks us to determine tension 1 in the lower cable and tension 2 in the upper cable as the hook and load are accelerated up at 2 meters per second squared, use g equals 10. So we'll come back here. Let's start with the load. That's the one that we're going to be able to find first because we can't figure it out. We can't figure out for the hook unless we know tension 1. So I know that my Fnet equals m of the load times A. A equals 2 meters per second squared. Mass of the load is 500 kilograms. So I know my Fnet equals 500 times 2. And that means that it is 1,000 newtons. Okay, my net force is going to be Fnet equals Ft1 minus Fg. We know Fg is, so 1,000 equals Ft1 minus 5,000. So Ft1 is going to be 6,000. Here. Okay, then we move on over here. And I'll put that 6,000 newtons in that free body diagram as well. So we're going to use that same principle, that same Newton's law. Fnet equals ma, the mass of the hook. So Fnet equals the mass of the hook times acceleration. Mass of the hook is 50 kilograms, and the acceleration is 2 meters per second squared. All right, so that means Fnet is going to be Ft2 minus Ft1, the sum of Ft1 plus Fg. And that's Fnet. Okay, so the one that's pointing up, Ft2 minus the sum of Ft1 plus force of gravity. So we know that's 6,500. So we're going to say Ft2 minus 6,500 equals the mass of the hook, 50, times the acceleration, which is 2. So I know that's 100. So Ft2 is going to equal 100 plus 6,500, so 6,600 newtons. So it's not much bigger than the other one. All right, and as a reminder, let me just show you what the whole thing looks like. So yeah, this is probably a little long. I got a little crazy. Sometimes we have to go back and adjust after we actually get the numbers. Who knows? I don't know if that makes sense, but it should be about 100 newtons longer than these two together. Okay, next question. Two 10-kilogram boxes are connected by a massless string that passes over a massless, frictionless pulley as shown, aka an ideal pulley. The boxes remain at rest with the one hanging vertically and one on the left 2.0 meters from the bottom of an inclined plane that makes an angle of 60 degrees with the horizontal. Coefficients of friction, so kinetic friction is 0.15, static friction is 0.3, that's between the left box and the plane, because again, that other one on the right is just, this one here is just hanging. And then they give us, you can use G equals 10, they give you the sine of 30 to be 0.87 and the cosine to be 0.5. Okay, I'm actually going to do this out of order, and my apologies, because this says draw and label all the forces acting on the box that's on the plane, but without knowing what the tension is, we can't accurately do that. Actually, you know what? Let's just do it, and then we'll answer. Okay, I'm just going to zoom in on this because there we go. Okay, so I'll put it down below here. How big is that? That's pretty big for you guys. You got it. All right, so first I'm going to do the force of gravity. Force of gravity acting on that is going to be mass times acceleration, sorry, mass times gravity, mg, which is 10 times 10, which is 100 newtons. All right. Then I'll have normal force there, and we'll leave that for now. I'll also have tension, force of tension. And the last thing I'm going to have is force of friction. Here's the deal. This is at rest, so until I calculate the force of the tension, I'm not really going to know which way that static friction is pointing. So I'm going to leave that for now. What I am going to do is go over here and look at this guy, because here's another instance of force of tension right there. So I'm going to do his free body diagram. Remember, we're also at rest. Fg equals 100, because it's 10 times 10 again. The only other force acting on this is tension, so that means that that's 100. So I'm going to come back down here. I'm going to add in my 100 newtons. Okay, and now let's think about the components, because that's going to help us. The components of force of gravity, right? So there's this component and that component. All right, so we actually know that the component of the force of gravity that's pulling it down is not going to be 100, because the force of gravity itself is 100, so there's no possible way that its component is going to be 100. So force of friction will point in this direction as well. There's two ways. That's too long. This is, nope, hello. My bad. Just force of friction. They don't want the components. I added those in just so we could visualize. So there's two ways to actually calculate force of friction, which I think we do later, so I'm not going to do that right this second. Okay, so this, you don't have to have the 100 and the 100 on, but it's hard to do for the free body diagram, but it's hard to figure out which way force of friction points unless you figure out what the tension is. Okay, the next question asks us, what's the tension in the string? Great, we already got that, 100. And then determine the magnitude of the frictional force acting on the box on the plane. So using Newton's second law, we can say F net equals ma. We know it's remaining at rest, so we know that F net is 0. And we know then that force of tension would be equal to force of friction plus this down here, this component, which is Fg sine theta. And did they ask for the magnitude? They asked for the magnitude, yeah. So that's a pretty simple one to do. We can say the force of the tension is 100. Force of friction we're solving for. Fg sine theta is 100 times 0.87. And that gives us 100 equals force of friction plus 87. So force of friction equals 13. And again, it's the magnitude, so don't worry about the sign. Okay, so the string is cut, and the left-hand box slides down the inclined plane. We're going to determine the amount of mechanical energy that's converted into thermal energy during the slide to the bottom, and then we're going to determine the kinetic energy of the left-hand box when it reaches the bottom of the plane. All right, so we know for sure that this box up here has energy because it has GPE. So it does have some mechanical energy. Thermal energy is force of friction, or is work done by friction. So we just have to figure out how much work is done by friction. Kinetic. Force of friction kinetic is going to be equal to mu kinetic times normal force. All right, and then normal force, did I calculate? No. The normal force is going to be equal to this component, which is Fg cosine theta, which is 100 times the cosine of theta, which is 0.5. So this would equal 50. So our normal force is going to be 50 newtons. Okay. So over here, force of friction kinetic is equal to mu k, which is 0.15, times 50. I'm having a brain fart for a second. Is that right? That's right. Okay. So this will give us 7.5 newtons. Then after that, it says determine the amount of energy it's converted into thermal energy. So again, like I said, it's the work done by friction. That's going to be the force of friction, 7.5, times how far it moves, 2, so 15 joules. Okay, the last part of this question asks you guys to determine the kinetic energy of the left-hand box, the one sliding down the plane, when it reaches the bottom of the plane. So we know it doesn't have any kinetic energy. It doesn't have any kinetic energy up here. So let me just let's draw the free body diagram of this. We've got Fg, which is 100 newtons. You guys can't see that. Silly me. We've got normal force, which is 50 newtons. We've got force of friction, which we calculate to be 7.5 newtons. And again, that's kinetic, not the static force of friction that we had earlier. All right, that's it. That's the whole free body diagram. Don't worry about that part. I was just making my arrow a little smaller. All right, so the two forces that do work, force of gravity does work. A component of it does work, right? So like this component does work. That's going to do positive work because it's pointing in the same direction as the motion. This does negative work, which we already calculated to be negative 15. Okay, so I'm going to, this component is going to be Fg sine theta. So we're going to find that work, is equal to Fd, right? We also, okay, here's one thing. Work equals Fd cosine theta. That's the angle between the motion and also the angle between the motion and the force. So if this is Fg, the angle between the motion and Fg is not 60. That's the angle between the horizon and here. So this angle here will end up being 30. Okay, so if we want to use Fd cosine theta, we would need to use 30, not 60. So we can do that. W equals 100 Wg equals 100 times 2 times cosine of 60. Nope, 30. Oh my God. Okay, so that's going to be 50 times 0.87, which is going to be, that's 200, Julie. Wow, you guys. Which is 187 times 2, which is 174 joules. So that's the work done by gravity. The work done by gravity plus the work done by friction is going to give us our Ke at the bottom. The work done by gravity is 174. The work done by friction is negative 15. So that is 159 joules at the bottom for kinetic energy. The other way you could have done it is you could have just multiplied this component, which is Fg sine 60, Fg sine 60 times 2. So Fg sine 60 times 2. That would be fine too, because sine of Fg sine 60 and Fg cosine 60 or Fg sine 60 and Fg cosine 30 are the same thing. So you would have gotten 87 times 2 again. Don't mind that, guys. which is again 174. Last question. A 2 kilogram block is released from rest at the top of an curved incline in the shape of a quarter of a circle of radius r. The block then slides onto a horizontal plane where it finally comes to rest 8 meters from the beginning of the plane. The curved inclined plane is frictionless, but there is an 8 Newton force of friction on the block while it slides horizontally. Assume g equals 10. Determine the magnitude of the acceleration on the block while it slides along the horizontal plane. So what we know about the block while it slides along the horizontal plane is that force of friction is equal to 8 newtons that way. Normal force and force of gravity. Force of gravity is going to be 20. G equals 20 newtons. Fn equals 20 newtons as well. All right, so our net force is going to be 8. And to get acceleration, we do F net equals ma. Really, our acceleration is -8, but our net force is -8. But they asked for magnitude of acceleration. So again, magnitude is just a number. The negative would be a direction, so it doesn't matter. So I'm going to put my F net is 8. My mass is 2, so my acceleration has to be 4 meters per second squared. It's really going to be -4. They ask for magnitude. Okay. Then the next thing is how much time elapses. So here we go. Are you guys ready for this? Woohoo! So I'm going to do, this is kinematics. So I'm going to do an x naught, v naught, v, a, t. And here I do need to use the actual acceleration, not just the magnitude. So magnitude is -4. The time is question mark. When it stops, well, first of all, start, how much? While the box is, yeah, so it's just while the block is sliding horizontally. It's not including the time on the incline plane, or the curve, not the time here. Okay, so our starting x is 0, our finishing x is 8. Our v naught we don't know, but our v, this is where it would stop. That's a v of 0. All right, so let's write it out because this is a little tricky. V equals v naught plus at. V squared equals v naught squared. I'm just going to stop this. Why haven't I been hitting stop? Why have I been hitting snooze? Plus 2a x minus x naught. And then we've got x equals x naught plus v naught t plus 1/2 at squared. Okay, here's your problem. You're going to be like, I have to solve for t. I'm going to get this negative. But we don't know v naught, which is a huge problem because v naught is in bam, 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 all 3 of these. Okay, so let's circle back. Let's solve for v naught is what we really should solve for, and we're going to need that. We don't have t, so we can't use either of these two. We got to hope then pray that we can figure it out from here. So we're solving for v naught. Luckily, that's not an issue. Let's move over. Okay, so I'm going to say v squared equals v naught squared plus 2a x minus x naught. And I'll just plug in. So v is 0 equals v naught squared plus 2 times -4 times 8 minus 0. So 2 times 4 is 8. 8 minus 0 is 8. So -8 times 8 is -64. V naught squared minus 64 equals 0. 64 equals v naught squared. V naught equals 8 meters per second. Great. That is helpful. Okay, I love using this formula whenever I can. It's the easiest one, so let's go for it. V equals v naught plus at. V is 0. V naught is 8. A is -4. And then there's t. All right, so we can flip this over here. 4t equals 8. T equals 2 seconds. All right, this makes the last one very easy. It asks you, what does it ask? Calculate the radius of the thing. Great, so this is energy. And there's no friction on here, so we know energy is conserved. So we know up here there's potential energy, gravitational potential energy, and down here there's just kinetic. The reason that helps us is because the initial height of this guy is equal to r. So that's how we can figure this out. We can say the UG up here is equal to the K down here. So m times g times h is equal to 1/2 mv squared. Well, the m's cancel out. G is 10. Our height is r. And our v is the speed right here, which we called v naught in our kinematics. Our v naught was 8. So 1/2 times 8 squared. Whoa. Okay. 8 squared is 64. Half of that is 32. So 10r equals 32, which means the radius is 3.2, and the SI units for height is meters, so 3.2 meters.